Oh yeah, Mr. Man was gonna come.
Huh.
Okay, so we have 13, 14. And I know Olivia is not going to be here. Who else am I missing? Let me see the attendance here. Okay, so I have Trace. I have Trace, President Zoom. I have Miles, President Martin Zoom. Do I have Ben? Okay, I don't think I have Ben yet. So that's the first one missing. Then I have Sheldon. I have Victor. I have Katie. I have Sophia. Gavin. I have Jonathan. I don't have Olivia. And okay, so welcome. So the only person I'm missing that I wouldn't expect to miss is Ben. So we'll have to keep an eye out, see if he comes in. Okay, so today, what I said I was going to do, go over the quiz, the homework, teach the next lesson, and then look at the homework. Is Ben? Perfect. Okay, so let me get Ben back up. Okay, so, and then Wyatt, you're going to contact me tonight sometime, right? Let me know what the plan is.
Yeah, I will.
Okay, that sounds good. All right, so for right now.
Dr. Riley, I just sent you a message.
Okay, yeah, I saw that. Okay, so you still, right, so you're going to do that. So let's see. I think, why don't we hold off on you doing that? Because I don't want you to miss today's class, okay?
All right.
You can do this. What do you think about that? And then chat that to me. In the meantime, what I'm going to do is I'm going to put you and Wyatt in your own breakout room, okay? Let me just do that. Fine. Okay, so I'm putting David. And David, will you able to get another charger?
Yes, I do.
Okay, great. Okay, so I have David and Wyatt can go into the breakout room, and I will come and get you in just a little bit. Okay, so they're in the breakout room. Okay, so let me find a nice quiz to go over. Okay, so there are 3 different versions of the quiz. So let me go over this version. This is version A. And then if you want me to look at your version, I'll pull that up as well. So let me just share screen. Makes me recognize it now. Let me just get this out of the way. Okay, so can everyone see my screen? Yeah. That closed. And that closed. Okay, so I think that's good. Okay, so let me grab a pen if I want to. Oh, shucks. Let me try this again. Grab a pen. If I want to write anything else on here, I can. Okay, so key things. For this first one, if people made an error, what they did was they didn't do the chain rule, or they did the chain rule, but changed this to the chain rule. Okay, so another thing people did was not raise it to a power. So whatever version you had something similar in that you had to raise it to a power, one less than what it was originally, and then you also had to do the chain rule. And then when that was all done, you had to go ahead and evaluate it for a certain number. Okay, so just be careful with that. Overall, that was done okay. A couple of mistakes here and there. Okay, the next one, the issue that people had was either the chain rule with the angle or the chain rule with the trig function. If there's going to be a problem, it would be one way or the other. Okay, so just be careful about that. The unit values are pretty easy to work with, and that will get you where you need to go. So you have to take the power down, write the sine 2x, take the derivative of sine 2x, which is cosine 2x, and then times the derivative of the angle. Okay, third derivatives were handled pretty well. Your class did a good job with notation. Let me just tell you one thing. If you are given, say, Leibniz notation, if you want to figure out the derivative, you really need to take it out of that notation so that you can solve for it. So that would be the appropriate use of that notation. In the other class, I had this more than in your class. People were doing this kind of notation, and you cannot do that. Okay, this is not appropriate notation for Leibniz. What you could do is turn things into this, and then you're okay writing the derivative. So just notation is really important. It's the language of math. You've got to speak the language correctly. Okay, any questions on the first page? So those
Wait,
three.
so real quick, so for number 2, can you explain find the derivative for that one? Because I'm confused where the cosine 2x came from.
Oh yeah, absolutely. Okay, so if your function was y equals sine 2x, and this is the best way to write that, the derivative is going to be power rule. Don't touch this at all. Take that derivative. That's cosine 2x.
Oh,
Then
okay.
take 2x, which is 2. Okay? So I think if
All right,
you
that makes
do it first, it may trigger the correct response.
Yeah, I had another test, so it was like a different problem, but the same thing. It was cosine squared 2x instead of sine, but like I get what you're saying.
Yep. That's the problem. So you've got to make sure that you do the chain rule twice in this situation. Okay, so let's come over to here. Okay, so here this was handled really, really well. In past years, this was a disaster. So to get your average rate of change, that's just going to be change in y over change in x. Okay? Instantaneous rate of change is going to be the first derivative. And I don't think, if anybody got anything wrong, it was just little math errors here or there. I think you all had the concepts correct, which was fabulous. So that brings us to the physics problem. So if the ball's thrown straight up in the air, that means that this must be a position function. So if it's a position function, what you're going to do is to figure out how high it is after 2 seconds. They're asking you what's the position in 2 seconds. So just evaluate the position function at 2, and then use your units, and you're good to go. Okay, when during the descent is the height of the ball 100 feet. So you see it is 100 feet 2 places. But I said during the descent, so So you're gonna pick the second one. So this is where factoring comes in. Okay, you have to know how to factor. And your first time is on the ascent, your second time is on the descent. Okay, what's the velocity after 6 seconds? So you have to know that velocity is the first derivative and then just evaluate it at 6 seconds. And I took it with a negative or without a negative. Technically, the negative is telling you the direction, but that's a fine answer for our class. Okay, so then they get, so this is the what question, okay? This is the what, so they want the velocity. Here's the when question. They want the time. So when is the velocity 60 feet per second? You know the velocity, so plug it in over here. Here's your first derivative. Solve for the time, and you should get 1.25 seconds in this example. But it's the same procedure as in the other versions. Okay, when does the ball hit the ground? You can come back and you can kind of, harken back to this function. It is starting up and then going down. These starting points and the end point are end points. So therefore, set your derivative, set your position function equal to 0 and solve, and look what you get. You're going to get 2 values, okay? So the best approach would be to factor out a 4t. So I factor out a 4t, I then get 25 minus 4t. Okay, so that means at time 0 is on the ground, that's this one, and then at 25 equals 4t, or 25 fourths, it's on the ground again. That's the second value. Okay, factoring is a good way to do this. Because technically, if you divide by t like this, you drop a root, and you're not seeing this root. So that doesn't hurt for this problem, but in general, it's better just to factor and then evaluate what the roots are. Okay, and the last question is about acceleration. So what you should notice is that when you take the second derivative, you do not have a t variable in there. So that means that derivative is always forever and ever negative 32 feet per second, no matter what time it is. And that's because the only thing acting upon that wall is acceleration. And it's always negative 32 feet per second squared, and that's from gravity. Okay, so that's what's happening there. So it is negative 32 feet per second squared. The negative tells you the direction. Second squared is what you want. Some people have issues with the units. But I think, and that's it then. So that's the quiz. So there are 2 other versions. This was version what? A. Does anybody want to see any of the other versions that maybe I need to clarify it in your version? So Miles, is there anything else on your version that you want to see? Does anybody else want to see a different version? Okay, if you want to see me work on yours and you want to do it with just you and I, just let me know when, and I'm happy to Zoom you. So don't be shy about that, okay? So people did well, but you can always do better and have a better understanding. Okay, so that's the end of that. So let me stop sharing here. Let me get our gentleman back. Okay, then as they're coming back, I'll go over the homework. We'll look at that. Okay, so I'm gonna go over someone's homework and I'll hit the high points. I'm just waiting for my guys to come back. So I have Wyatt back, I just need David. Okay, so David, you're back also. Okay, so I'm going to write to David. Okay. All right, so let me go and I'll share screen again and we'll go through this assignment. So this is the assignment after the quiz, and I wanted to have you go through those 6 categories of evaluating functions to kind of start into the calculus part of things, where we start really looking at functions in terms of their derivatives. So let me share screen again. Okay, so the top of the page has the 6 characteristics you're looking for. So a couple of things I wanted to hit upon. So in terms of when they say min or max, if they're talking about min or max points, you need to give me the coordinate pair. Okay, so when they say, let me just get my pen. Okay, so when they're talking about increasing, decreasing, you're speaking about what's happening to the y function in terms of x. So it's increasing from negative infinity all the way up to, this should be 1/2 here, because this is 1 here. So all the way up to 1/2, and then decreasing from 1/2 to infinity. Okay, so talk about your x's. They will tell you what your function's doing. Make sure you don't use a bracket over here. You've got to use a paren. Okay, so this is a parabola. There is no minimum because it goes on forever and ever, right? Because there's no endpoints there. And the maximum is going to be right here. And if they ask me for the maximum points, which I do for 1, you've got to give me the coordinate pair. Okay, max value for number 2, just give me the y value only. Okay, so know the difference between a maximum and minimum point and a maximum and minimum value. Okay, this function in terms of concavity, it is always going to be concave down. Okay, it's concave down throughout its domain. So there's no inflection point, so you're going to just say it is concave down from negative infinity to positive infinity. And then that takes us, that's 3. It doesn't have an inflection point because there's no change in concavity, so therefore no inflection point. In terms of the X-intercepts, I'm okay if you give me coordinate pairs or just give me the actual roots themselves. Unless I ask more specifically, I'm okay with either way. There is no undefined points and there are no asymptotes here. Okay, so that's how that's going to work for all the parabolas. So I'm not going to go through all the parabolas. This is not a parabola, so we're going to do this one too. So any question on the parabola type things? Okay, so then for this guy, we're going to do the same approach. So this is, let's see, the function is increasing from negative infinity to probably about, say, negative 1/2, I think is what I said. So I made this negative 1/2. Okay, and then it's going to be decreasing the rest of the time. Okay, so it's decreasing from negative 1/2, and then because it's going all the way to the right, it's going to be decreasing the entire time. So make it negative 1/2 to infinity. So this is negative 1/2. Okay, the max is going to be right here. It's a little bit off of 0. So I said my max is going to be -1/2, 5, to make that -1/2. Okay, the min, there is no min because these are both going forever and ever. The max value is just 5. Okay, this right here is an important feature. That is the inflection point. That changes and tells you where the concavity is changing. So from -infinity up to, but not including 3, it is concave down. From 3 to +infinity, it is concave up. Okay, so don't include the x value of the inflection point, because at this inflection point, it is neither concave up nor concave down. Then X-intercepts and Y-intercepts, you have one of each. So you write those down, and then you would you don't have any undefined points and no asymptotes. Now you could give some credence to the fact that this could be an asymptote. If you chose that as an asymptote, that's fine. It's really a judgment call as to whether it looks like an asymptote to you or not. My purpose of grabbing this particular figure was to get you the inflection point so you can see it. Okay? All right, that brings me to this. Okay, so here is something that's going to be changing direction and changing concavity. I picked this point right here to be the inflection point. So that is at 1, 3. Then I said this was my min and this was my max. Those are, by the way, relative mins and maxes. Let me just look at what I'm doing. Okay, so you're decreasing from -infinity up to 0, not inclusive, and then again from 2 to infinity, not inclusive. You're increasing in that in-between world from 0 to 2, non-inclusive. Your min is 0, 2, your max is 2, 4. And then for question 2, the minimum value would be 2, maximum value would be 4. In terms of concavity, this is what's going on. We are concave up from -infinity up to 3. Up to, hold on a second, up to 1, sorry, that's the other problem. So up to 1 is concave up. Then it's concave down from 1 to infinity. And your inflection point is at 1, 3. Okay, so question 4, you can easily spot the X and Y intercepts. There are no undefined points and no asymptotes. Okay, so the big thing here is recognizing you have 2 concavities, no more changes, and being able to use your interval notation so that you don't include the x value of the inflection point in your interval. Same thing going on here. So this point is 1, 1/2. That's your inflection point. So that means that your concavity is going to change. It's going to be concave down from -infinity up to the x value of 1, and then concave up from 1 to infinity. And then my inflection point will be 1, 1/2. I think everything else is probably good. You have a max, it's a relative max. You have a min, it's a relative min. This goes on and on forever. No asymptotes, no undefined points, 3 roots, and thankfully just 1 Y-intercept. Okay, so I'm going kind of fast through this. So my big push was these inflection points. So here's your inflection point at 3, 3. So your concavity is going to change on either side of that. So you are concave down from -infinity to 3, concave up from 3 to infinity, and this is how you would express your intervals. This particular function, you are always, always increasing. So you're increasing forever, you're never decreasing, but notice that the slope is initially very steep, and then it kind of flattens out, and then it goes more steep again. So you've got some changing slopes going on there. So you would never say the slope is increasing. You would just say that the function is increasing. That's a really big difference. Okay, the last one, or this last one here, I finally put in a asymptote, and it's the line y equals 4. So that's your horizontal asymptote. And there are no undefined points. Well, I guess technically there are. So undefined points, there's no points to the left here. So this is 1. So you could say that your function's only defined where x is 1 or greater. So therefore, it's not defined where x is less than 1. Okay, so I would probably say that was undefined. And then you've got an asymptote. You do not have any x or y intercepts. This is an absolute minimum. And this technically is your maximum. Even though it's not a vertex, that is your maximum. Okay, and your concavity changes right here at the inflection point. So that's 1, 2, 3, 4, 4, comma, probably 3 halves. Okay, so it's concave up to the left of it, concave down to the right of it. So that's all I want to say about those. You may need to go back and kind of rethink some of yours if you were missing some components. So then you absolutely want to know how to analyze this. So in terms of looking at it, it would be wise to first kind of write some things on it. So this is a max, this is an inflection point, this is an inflection point. Okay, so which label points is the function increasing? So CF, so when I start asking people things, because otherwise it's really boring just to listen to me. So Miles, I'm going to come to you. What do you think about the answer CF to the first one? At which label points is the function increasing? That look like increased points, Miles?
Yes, so I thought it started increasing at B.
So B is right. So at the min, it's neither increasing nor decreasing. So just eliminate B from your answer, okay?
Okay. So I guess then yeah, C and F.
Yeah, so C and F are good. Okay, that brings me to Jonathan. So Jonathan, at which label point is the graph concave up?
I also had B and F, but then I also had A.
Yeah, I agree. So pop A in there because A is also concave up right there. Okay, so the points that you cannot include, you can't include the C because that's an inflection point. It's neither up nor down, it's changing. Okay, so which level point has the most positive slope? So Maisie, what do you think? Maisie, can you hear me? So Heather, why don't you defend your rationale? So why do you think that's where the most positive slope is? Oh, come on, gang. Heather?
Yeah, I don't know. I thought it had to do with like the steepness. I don't know.
It does. So what you need to know is that inflection points are always the steepest part of your curve. Always, always, always. So E is the steepest positive, and C is the steepest positive, and E is the steepest negative. That is a very important characteristic of inflection points. So that's good. You want to definitely say that. Okay, so then let's go on to 18. At which label point is the function decreasing? So what do you think, Victor? We have A and E here. What are your thoughts?
I'd say that it's only D through F.
So first off, it can't be decreasing at D because that's a maximum point. It's neither increasing nor decreasing.
Okay. Then I would say E through F, but it starts concaving up when it.
Right, so F is
Right
decreasing.
there.
So look over
Yeah.
here. Pretty good, I agree. E is an inflection point, and it is a place where the function is decreasing. But look at A. Isn't that decreasing?
Yeah, A through B.
So I think the A and the E are good answers. Okay, does that seem reasonable? Okay, Gavin, we're coming to you for 18B. At which labeled points is the graph concave down? So what do you think?
I said C, D, and E.
Okay, so you can't say, so at inflection points, the concavity is neither up nor down. So that's going to eliminate C because it's an inflection point. It'll eliminate E because it's an inflection point, and it will leave you with D, which is correct. Okay, so on areas where it's concave down, don't include your inflection points. On areas where they're asking where the slope, the function is decreasing or increasing, don't include your mins and your maxes. Kind of the same idea. So at mins and maxes, the function is neither decreasing nor increasing, and at inflection points, the function is neither concave down or concave up. Okay, so don't include those inflection points, and then you'll be good to go. Okay, so that brings us over to some sketching. So I think I missed the last one, so hold on. Oops, we cancel that. We go over here, and let me not do that either. Okay, so we have sketches down here. So if the function and the slope are both increasing, I think you may want to have it kind of like that, so that you avoid having a flat area here. So those are both increasing. So the function is increasing and the slope's getting more positive. So the slope is also increasing. And I think to have it be, yeah, I agree with this. If the slope is going to be decreasing, it has to be steep here and then getting less steep. So the slope is decreasing, but the function is increasing. So we're going to go over this again in today's notes, but these are good things to be able to visually represent. Okay, so then we have 21, the function decreases and the slope increases. Okay, so your y's are going down, so that's easy to spot. Your slope is getting steeper negatively, so that means that the slope is decreasing and not increasing. So for this one, a better answer would be go this way, because here your function is decreasing, and here your slope, because it's negative, is getting less negative, so it's increasing. So remember that if this is like -5, and this is -2, -2 is bigger than -5. So that's why the slope is increasing to go that way. So don't go this way, go that way. Okay, and then for this one, it's going to be flipped as well. So you want the slope to decrease, but the function is also decreasing. So here, if you go like this, what's happening, say this is a -3, and say this slope is a -7. Well, that is also decreasing, right? So both the function and the slope decrease as x increases. So as you go to the left, x is increasing. Here, this value, say, was, I don't know, 10. Say this value was 2. So that qualifies that the function is decreasing. And then given those negatives, the slope is also decreasing. It's getting more negative. Okay, and this, I know this one's a little bit hard to draw. The idea is at 2, so about here, you want to kind of have an inflection point. So if you're kind of increasing like this, well, let's see, you're increasing like this, right, exponentially initially, and then you're still increasing, but you're going at a decreasing rate. So that's what you want. You want to have something like that. You have an exponential until you take the medication. Then it's still increasing, but at a slower rate. Okay, and then you have a max at the 3rd hour, and then you're going to decrease. Okay, so everything else is good, but I would just have a little bit different curve on your graph. Okay, so that was a lot of talking on my behalf. So anybody have any questions about this? This is kind of the foundational information we're going to build on in the next notes. Okay, so let's I'm going to save that. So look back over your work. This is the first time we're doing this, and the idea about slopes increasing and slopes decreasing, especially when they're negative, you want to go back over that. Know about the concavity, know that if it's concave down or concave up, things are limited where you have an inflection point. So that means you want to be careful about not including that with a bracket, just have it with you with a paren. Okay, so what we're going to do now is do chapter 2. I'm going to have to erase all my old chapter 2. So while you get your stuff out on notability, I will erase some of this so we can go back over it. So we did 2-1 together. So that's okay. But now I want to do this together as well. So let me just make believe this never happened. And then we can talk about this. And what we're going to do right now is we're going to figure out first and second derivative meanings, I guess we'll say. Meanings in terms of how they impact what you are graphing. And so eventually, when we take a quiz on this, it's going to be not a calculator quiz because you're going to be doing a sketch based on information that you've received and not on your graphing calculator. So we'll be talking about how you can determine things based on your values such as your slopes, your derivatives, all those good things. Inflection points, all those things are important. Okay, so almost done. Oh, okay. There we go, and I think, yes, so then I'm going to erase this. This is my favorite page. We'll do this one together. All right, you ready to go? I apologize for all the direct instruction today, because sometimes you just have to do it. Okay, so here's 2.2. Let me just get my notes out. Okay, so 2.2 says it's all about first and second derivatives. They talk about derivative rules, and we're going to end up doing derivative tests very, very soon. So your first derivative rule, if the first derivative at some point A is positive, then that means your slope is increasing at x is A. If your first derivative at A is negative, then your slope is decreasing at x equals A. So they said, go ahead and draw a picture of that. So they want us to draw an example of a function with, at some A, the slope is greater than 0, so it is positive. So I need a positive slope. So what if I did something like this? Here's my function, and if I pick that to be my A, then if I draw a tangent line there, I can say that yes, at A, my function is positive, so that satisfies that. Okay, so that's what you're going to be doing. So the next one is just the opposite. At some A in question, the slope is going to be negative. So let's see, if we just have it downward sloping, right? You can even make a line and have it be negative the whole time. Here at my A, this is f of x, and this is x, and then A is a special x. My slope is indeed negative, so that sketch satisfies that requirement. Now, this is what, so up and down on this is what we're doing. But now this is what we want to look at. This is a mini example of what we're going to be doing. So first off, there are several things they're telling you. This is one thing. This is a second piece, a third piece, and a fourth piece. Okay, so the first thing they're telling you about is a point. They want you to sketch a graph that has these characteristics. Always do your points first. So without even reading anything else, I'm just going to put that point on my graph. So this is the x value is -1, so read it correctly. The x value is -1, the y value is 0. That's where I am. Okay, so that takes care of that point. Then I'm going to kind of look at everything all together. The next three pieces are all about slope. If the slope is less than 0, whenever x is less than -1. So that means over this way, my slope is negative. Then it tells me that the slope is 0, right on -1. And to the right of -1, my slope is positive. So what I have is a little parabola with its vertex right at the point identified. That's what's going on. Okay, so first get your point. That was the point. Then everything else, so let me do some different highlighting. Okay, this little piece, the slope is less than 0. That's this little piece here. And then we'll go green. This little piece is here. And here, this becomes a min. So what you have just learned, if you go from negative slope to positive slope, that's going to be a min. If you go from positive slope to negative slope, you've identified a max. And those are the kind of takeaways you want to have. Okay, that's the important piece of this. Okay, so that's one mini example of what we're going to do. So far in this section, they only discussed a point and the first derivative. So we're going to talk about the second derivative rule next. So let's do that on the next page. So here's your second derivative.
Dr. Riley,
Yep.
is there any chance you could scroll back up to 1 and 2? It was printing and I missed it.
Yep. Can you do that?
Thank you.
Huh? So your first and second derivatives tell you a lot about your function. They tell you about the second derivative function, but they also tell you about the original function, and that's what we're counting on here. So based on information about my first and second derivative and my roots, I can draw the original function. Are you good, Gavin?
Yeah.
Down here. Okay, so here's Mr. Smiley and Mr. Brownie. They come in very, very handy. Okay, so second derivative. If the second derivative is greater than 0, so that would be this case. Second derivative, second, so I give 2 pluses, greater than 0, I'm going to have a situation that's concave up. If my second derivative is less than 0 at some a in question, so if it's less than 0, it's negative, my situation is going to be concave down. Okay, so this is an important thing to keep in mind. It will really help you understand. If things are positive, you're smiling. If things are negative, you're frowning, and a frown looks more like a max, and a smile looks more like a min. So they want us to now do the same thing we just did. Sketch these 2 examples. So the second derivative is going to be greater than 0. That's positive. So I need you to sketch something that at A is going to be concave up. So you can just do a little parabola, and that will do it, because this particular parabola is always concave up. Okay, so that's an example of concavity, and it's concavity up. And it only has one concavity, And there are other sketches you could have done that would have been as correct. Okay, the next one says the second derivative at some A is less than 0. Less than 0 is negative. That's going to be concave down. So go the other way with your parabola. Here's your A. Here it is. I can see that it's concave down throughout its domain. So therefore, it certainly is concave down at the x value of A. Okay? All right, so we'll get to have a little bit more fun as we go through. Okay, the next page I just took directly from the textbook. I'm just going to kind of read it through. I thought it was a very good table. That's why I took it just in its entirety. So you can have all these different conditions. So there's 4 different conditions that they're explaining to you. So what I liked about this is they first told you, okay, f prime of A is positive. In terms of the function itself, it's going to be increasing. So a positive f prime of A is making the function be increasing. Okay, so that, and this is the sketch of it. Simultaneously, if you took the second derivative, it would also be positive. And the reason why it would be positive is because positive tells me concave up, and this picture is concave up. Okay, so both of these things are going to hold. If your first derivative is positive, as I said before, the function is increasing. But having a negative second derivative makes it concave down. And this is the resulting u. Okay, then they go negative. What if your slope is negative? Whenever you have a slope is negative and your function's decreasing, if your second derivative, however, is positive, positive is concave up, you've got to turn it that way so that it's concave up. And then do the opposite for the next case. The function's negative, so it's decreasing, so the function is decreasing. Remember, don't ever say the slope is decreasing. And it's going to be concave down because the second derivative is negative. Okay, so here's the first bit of fun. And then we'll get to my favorite graph. Okay, so I'm going to give you a few minutes to see if you can figure out what you're going to sketch. So Montgomery County has decided that it's not safe for kids to be in school until at least March 15th. Okay, that's an advisement. It was February 1st, currently it's getting dangerous out here. Okay, so sarcasm noted, but we're here. We're doing it. Okay, so these are 6 different properties. This little line kind of had a minus sign and hopped over here. But what I want you to do is read each of the properties and then write down what that tells you. And then we're going to get a sketch going. Okay, so I'm going to be silent for a little bit so that you can write down some stuff. And then I'm going to call on you as we go so that we can make sure we're pulling this all together. as we start discussing it, I'm going to call on people to give me their insights. So the first property, it says the function is defined only for x is greater than or equal to 0. So Sheldon, what does that tell you?
That's increasing.
Not necessarily, it's just telling you a location. So where are they telling you that the x's are?
It's past 0.
Greater than or equal to 0. So what quadrants are those?
Oh, quadrant 1 and quadrant 4.
Excellent, excellent. Okay, so kind of get an idea of where this graph is going to be living. Okay, so then look at number 2, and Katie, they give you 0, 0, and 5, 6. So what does that tell you? So what are those things? I don't think we have Katie. Trace, can I hop over to you? Trace? Sophia?
I said that the first one could be an X-intercept.
That is. Okay, so what bottom line is these are both points, right? So the first one is not only an X-intercept, it's an X and Y-intercept, right? This is right there on the cusp.
Yeah.
Yeah, so they're points. So if I say that they're points, I know that I have to graph them, okay? So I'm going to say must graph. Because when I grade these kind of assignments, I grade for each of the properties, and you'd be surprised at the number of people that don't put the points on. That's the easiest thing. They spend so much time doing everything else, they forget they have to do those points. So you're gonna must graph them, they're your landmarks so far. Okay, good. Okay, so number 3, Ben, can you comment on that? The slope of x is greater than 0 for x is greater than or equal to 0. So how about y? And how about David? Okay, so let's see. Heather, could you be able to assist?
It's a positive slope for that section when x is greater than 0.
The slope is positive, and that means that the function is increasing, right? Okay, so there's 2 things we have. The function's increasing, and the slope is positive. Okay, number 4, Mason, I'm going to just call on you because I know you were sure of that. So what do you think?
It says concave down when x is less than 5.
Right, because it's concave down. So concave down when x is less than 5. Good. Okay, how about when f prime of 5 is 0? What does that mean? Jordan, Kurt, are you with us? Okay, Katie, back over to you. And on to, let's see, Miles, can I come back to you?
Does that mean when x is 5, y is 0?
Doesn't have to be. It's a second derivative. So when the first derivative equals 0, that's a max, a min, or a shelf. But when the second derivative equals 0, what is it?
Does it relate to the concavity of it, or?
So it's the place where concavity is changing. So what's that place called?
The not the intersect point.
INF.
I'm drawing a blank here.
No, it's okay. INFL.
Inflection point. Inflection.
Okay, so that's important because I know the concavity is changing there. Okay, so then we're down to the last one. So, Wyatt or David, are you there now? you know. Okay, hold
I'm
on.
here, but I'm just still trying to learn and figure it out because I'm not sure I have a complete understanding of the concept yet.
Okay, and Katie, you're good too, just hang in there. Okay, so I'll take that one, I haven't taken one yet. So if the second derivative is greater than 0, then I must be concave up when x is greater than 5. Okay, so then let's go ahead and let's try to get a sketch. So first thing, always put the points on first. Okay, so here let's just say this is 5, and let's just say this is 6, just for ease of sketching. Okay, so what I know about the inflection point is that it's happening where the x is 5. So it has to be happening here, right? Because it has to be on the curve. So that's the inflection point, which is great. I also know other things. I know that to the left of that inflection point, my function is concave down. So it's concave down here, and then it's concave up here. And that could be a good sketch. Okay, so that represents a graph that will answer all 6 of your features here, all 6 of your properties.
I have a question.
Yes, go ahead.
So for number 5, when it says the second derivative is 5 is equal to 0, like what? So I know that the second derivative relates to the concavity, but what does like the 0 mean? Does that just mean like it's not moving?
So if it's 0, then that means it's neither concave up nor concave down. You know?
Okay.
So you say it's concave up, you can't say it's concave down. So it's not a question of moving, it's changing. At that exact instant, the concavity is changing from being down to being up. So therefore, it does not have a concavity value.
So would there ever be something where it's like second derivative of a number equals like 1 or 3 or something like that? Or
They said that, couldn't they say that, let's say for point 4, they could have said f prime prime of 4, right? They have to make that a 4 instead. Make this a 4. Instead of saying less than 0, say it's -3. Okay, so that's going to give you an idea that it's negative. So they can be more precise. They gave you the fact that through the entire area here, less than 5, it was always going to be concave down. And then you got to the inflection point, and then all the way here, it was always going to be concave up. But they could have just given you the second derivative of any point along the way, and you could have kind of, figured that out. It would have been more information.
okay.
Okay? So this is an example of what we're going to be doing. But I want to get to my favorite slide because this is really important and it brings everything together. It'll give you a slight headache, but then it'll go away and it'll be okay. Okay, here is all 3 functions. You've got the first derivative of the original function in blue. You've got the first derivative in red. And then you have the second derivative in green. Okay, so that's what's going on in this curve. Now, important things. Let's look at the first derivative first. Do you see how, look at the original function first. Do you see how this is a max and this is a min? Okay, so then, if it's a max, what I know is that that slope has to be 0. What gives me the slope? The first derivative gives me the slope. Look at the first derivative value. The first derivative's value is going to be read off of the y-axis, and that's going to have a value of 0. That indicates that it is either a max, a min, or something called a shelf that we'll get to eventually. Look at the min. That derivative will also be 0, and therefore, reading the red, it's going to be 0 right there. So I can read at an x value of 10, my slope is 0, so I'm going to read my slope off of the y-axis. So those things line up. Then, what other points are interesting? How about if we look at the place where concavity is changing? Now I know somewhere in here, say, somewhere in here, it's going from concave down to concave up. If I only have that original function, I cannot tell where that's happening. But if I look down at my second derivative, and I find where that is 0, which is happening right here at 6, I now have information that I need. I now know that where x is 6, which is right here, so let me just get rid of those colors, that is going to be my inflection point. It lines up with a second derivative that has a y value of 0. Okay, other things. Look at the first derivative where x is 6. Do you see how on the original function, where x is 6, that is the steepest part. If it's the steepest part, it's going to have the greatest slope. That is the steepest negative part. So therefore, it has the greatest negative slope right here, and I would read it off of the y-axis. So that's how I'm relating inflection point on the original function with a minimum on your first derivative and a root on your second derivative. Okay, let's talk about concavity. I know the function is concave down from a y value, an x value of 0 all the way to 3, all the way to 6. Since that's the case, do you see how the second derivative is always negative there? It's below the x-axis. The concavity then becomes concave up when I move over to values of x greater than 6. And therefore, right here, my concavity, which I read off of the y-axis, is always going to be positive, which indicates it's concave up. Okay, other things. So things, big picture things to notice. So let's describe the functions. Okay, the first function, which is the original function, that is a cubic. Okay, so this is going to be a cubic. The first derivative is 1 power down from it. Therefore, that is a quadratic. And the second derivative is 1 power down from there. Therefore, that's going to be a line. Okay, so if the original function was a quadratic, then the first derivative would be a line, and your second derivative would be a point. So that's how that's going to change depending on what your power structures are. Okay, so other things you want to know, the cubic function has a max at 2, 9. Okay, and it has a min at 10, 1. And it also has an inflection point at 6, 5. And I can get those exact values because I can line them up with the other derivatives. As a parabola, the inflection point is noted, has an impact on that first derivative, and it yields a minimum at 6, negative 1.5. Okay, the line, notice that the slope is always positive of that line, and it has a 0 at 6, 0. So you can analyze the functions alone after you've analyzed them together, because then you can truly tell where you have things going on. Okay, so you might probably want to spend some time with these 3 functions, because it's really important to get a good handle on how one original function can result in a unique first derivative and a unique second derivative. Okay, so there we have it. So those are the notes. So going forward, I'm going to have you do a lot of this stuff. The assignment tonight is just to analyze. I'm going to draw for you the original function. You will then draw for me the first derivative, and there'll be the one problem that will have a first and second derivative requirement. So let's take a quick look at that homework. Before I do that, anybody have any questions on anything I just went over? Because it's been a lot. And we're getting ready to do some calculus tests to figure out what our functions are and what they look like without being actually given a function to work with. So up to this point, I said find the second derivative, and you would just take it. But if you don't have a function, you've got to figure it out based on other information. Okay, so let me get out of this, and I'm going to go into here and go for the assignment for today. Okay, so this is your job. So you have to do some factoring. I'm going to give you a parabola for the first 3 problems. You're going to find the exact width by factoring, find your derivative, find the x-coordinate of the vertex using the fact that f prime of x is going to equal 0. Okay, so you're going to get it exactly. So let's do some of this one together. First off, you're going to be doing some factoring, and hopefully you can do hard factoring. So you say to yourself, it multiplies to 108, to negative 108, and adds to negative 23. And I ended up, maybe I have to do this. Do I have it? I don't think I have it. Do I have it? I think I do have it. Let me go back to notability, because I think I have it up here. Let me just see. Yes. Okay, so this is it. Yes. Okay, so in terms of finding the exact roots, what I got for my roots without belabeling it was 3x plus 2 times 2x plus 9. So get that any way you can. So then next thing you're going to do is take your first derivative to find your x-coordinate set equal to 0, and you're getting 23/12. Look up. That looks right. It's right about 2. Equation of the tangent line you have to know. If they give you an x of 3, plug in the 3 into your function, get your y value. Take the first derivative, plug that in, get your slope. In terms of the concavity, take the second derivative and look what you see. It's always positive. It's always positive, it's concave on. Parabolas never have inflection points because they have an inflection point. You set the second derivative equal to 0, and 12 will never equal 0. So that gives you a little intro. So then in terms of previewing, this is another parabola, another parabola. Here's find something more interesting. I give you the factored form. You're going to see there's going to be an inflection point someplace in here. You can figure out exactly where it is by setting the second derivative equal to 0. You'll have an inflection point. You have a max and a min. In order to get your roots, Notice that they are crossing at like strange places. I wanted you to use the quadratic formula because it's not factorable. Okay, so that's it in a nutshell. So, and then for the ones with parabolas, the last step I asked you to do is to sketch the first derivative on your graph. For this one, I asked you to sketch the first derivative and the second derivative. You've got the formula, you can go ahead and just plug it in and figure out where it's going to be. I tend to use the y-intercept, and then I tend to look and see where my root would be, and that's based on the previous function. So think about that, and that's all I have. So I know it was a lot of direct instruction. I'll do less of that next time, but I just need to get a lot of material covered. So I hope I didn't bore you to tears. So any questions for the good of the cause? Nothing? Okay. So Wyatt, I'm going to hear from you. And David, I'm going to hear from you as well, correct? Hopefully that is correct.
Yes.
So just email me, okay?
All right.
My people at home, I can let you go because I've asked a lot of you. So you may run out, and I'll see you next class.
Thank you.
Dr. Riley.
Thank you.
Thank you.
Thank you.
Thank you.
Okay, so Trace and Jordan, where have you been the whole class? Oh, we lost Jordan.